Yes, we'll start with Monisha Ghosh first.
Okay. Thanks, Kaushik. While we wait for the slides, I must say this has been a very interesting discussions so far. We have a nice group, and hopefully what we want to do is start off and each of us will take a few minutes to talk about some of the work each of us are doing with different kinds of data sets, and then try to have a discussion about what we think are the needs of data sets, and how to progress further on this. So these were the top questions that were given to us by Kaushik, I guess. I don't think we're going to go specifically through each question as listed, but they are kind of in the back of our minds as we talk about the work we're doing in this area. So it was the state of the art and gaps in software tools and APIs for data collection. I think all of us have worked with data at some point. Can we standardize metadata representation for diverse RF use cases? We talked a lot about that, I think, in the first session. And question number 3, ways to encourage community engagement. For the purposes of this panel, let's set aside the privacy discussions that we had before. Let's assume that we can do this, we can all go out and collect data. Then how is it that we can encourage more groups to not only collect data, but share it among ourselves? So I'll start with a few slides about my viewpoints on this. There are multiple challenges still with collecting real-world data. When I mention real-world data, I really mean either from an experimental testbed over the air or in the wild data from deployed networks. As we've talked about a number of times today, there are diverse data types. We focused a lot on IQ samples, which very quickly can get into the exabytes range depending on your bandwidths and the frequencies that you're looking at. The next level down, I think, is spectrograms. So a lot of the spectrum sharing situations that, especially in Spectrum X, which is the NSF Center for Spectrum Innovation we are dealing with, maybe spectrograms are good enough for a lot of the spectrum sharing and coexistence issues that some of us deal with. And they generally are already processed, so they require less storage, and there are probably less privacy concerns around spectrogram data compared to IQ samples. And then finally, there's a lot of network-specific data. So today you have access to a lot of tools that the cellular operators use, which are also available to us as researchers, where you can grab the higher level data on a network, the RSRP, which is the reference signal power, the quality, the channels. So there are for example, Wi-Fi cards where you can extract actually the multipath channel parameters. You can run throughput tests, latency tests, etc. These are all collectible fairly easily today using APIs on smartphones. There are a lot of commercial tools that cost a pretty penny, but they're still very good. Or there are a lot of tools developed by the community. Some we've developed. There are other people in the community that have developed tools that allow you to go out and collect your own data at that higher level. There are many diverse needs which are all different. They require different kinds of data, and we've heard about that also already today. Channel modeling is, NIST is, of course, the gold standard of how they do channel modeling very accurately. They set up their antennas, their entire chain. Depending on what bands you want to do, low, mid, or high bands, you will end up with very different data sets and types of channel modeling. The problem that I think we as a community need to start looking at is what's in the future. So we've really focused on sub-6 because most SDRs were sub-6, and there's been some work in millimeter wave. I also sit on the FCC Technological Advisory Council on the Advanced Spectrum Sharing Working Group. And one of our tasks is to look at 7 to 24 gigahertz. What is there? Are there bands in there that are suitable for sharing? And those are difficult bands to characterize. Firstly, because you don't have a lot of SDR, so you're really resorting to spectrum analyzers or going out there and capturing data on other kind of generators. And maybe, so that all these bands are allocated. Just because they're allocated does not mean they are being used. So understanding what the spectrum uses in that band is a challenge. Um, I'd want to point out a little bit of difference between channel modeling for your system versus interference modeling. I think a lot of what we've done as a community has been channel modeling. So for example, if you want to do a millimeter wave channel modeling, you set up your transmitter and receivers, you point the antennas towards each other, and you take your channel measurements. Interference modeling is actually the opposite. Your antennas are not aligned. You don't know where the interferer is. You don't know where the incumbent is. And so figuring out how to do interference modeling right is a problem. And more so because there are so many different interference scenarios and more waiting in the wings as we look at 7 to 24. So we've heard a lot about radar and cellular and C-band, back in January when the C-band spectrum was going to start being used. There's microwave and unlicensed in 6 gigahertz. Yes, FCC has rules for that band, but the interference concerns still remain. In CBRS, there's a new type of interference that is emerging, which is not CBRS and radar, but secondary coexistence between two GAAs. This is not a problem that has been studied before. So how do you gather data to characterize and understand and then propose solutions for that problem? And then in Spectrum X, we're very concerned on the passive uses of spectrum, so the radio astronomy, mobile wireless. Each of these scenarios require very different kinds of data, different kinds of capture. And so the question is, can we even come up with one way of attacking all these problems? And finally, we've talked a lot about AI, ML research. Data needs are very specific to the application. So if you're trying to do RF fingerprinting, you're looking at a very different kind of data set than if you're trying to do automatic beam selection for millimeter wave, for example. And so I think as a community, we probably have to try and figure out, classify the kind of data we need and try to see what are the best practices for gathering data, sharing data, and using data in all of these. So these are, again, my thoughts on what data to collect and where. In my mind, there are 3 ways that one can approach this. One is the experimental SDR-based test beds, such as power. The pros of this is you have full control of the experiment. Everything is software defined, and the type of data you collect is under your control. The cons is it can be very difficult to replicate the complexity of deployed networks, especially the interference scenarios that I just mentioned. A cellular system network today is really complex. There are many channels being aggregated of varying bandwidths. It's changing on a milliseconds basis, literally, with every resource block. And the realities of propagation channels in diverse environments like urban canyons is difficult to replicate on a single test bed. There is also the problem, as we are discussing in one of the conversations, about just getting on the air. So just getting a lot of these experimental platforms, notwithstanding that they're all in innovation zones, just getting on the air is tough. The second extreme is deployed networks, which is something that I've personally been doing in my research, is just leverage what's out there. Treat your city as your test bed. All of the carriers have dense deployments in cities, rural areas, urban areas. There's millimeter wave, C-band, CBRS, LAA, you name it, it's all deployed. It's tough to find it, but once you find it, you can start taking measurements in the wild, so to speak. The cons, of course, here is we have no control over the other end. We have control on the receiving end. We don't have any control on what the operators are doing. And there is a middle ground, which is something which I'm trying to pursue, is we deploy networks using commercial equipment, but we use it with some kind of flexibility, and then we use industry standard tools for capturing the data instead of doing it the old-fashioned way with SDRs. So for example, if you want to deploy a CBRS network today, if you go and buy commercial equipment, you can get on the air very fast. If you want to do it with SDR-based equipment, you have to go get an experimental license, which takes a lot longer. So can we figure out ways where we can set up networks as a community in some of these new bands that are coming up, the 6 gigahertz band, CBRS, and start taking the data that we need to do the work we do. So I have 2 pictures over there. The top one is, both of these are in my previous University of Chicago campus. So there is a Verizon installation on the 10th floor. It's a C-band installation, is line of sight to a UChicago building. I can set up an SDR, I can set up CBRS in the channel next to it, and I can take measurements, and it's not cost me a penny to deploy this, other than buying some CBRS equipment. The other picture down there you'll see is there's a millimeter wave pole very strategically placed opposite a dorm. And so we've done a lot of work on characterizing outdoor to indoor performance of millimeter wave using that location. Again, finding it and then setting up and capturing data in these specific locations. So we've written a bunch of papers. All of them have used real data from real networks. We don't make it publicly available like on a website. If anybody wants the data and they reach out to us, we will make it available. But I guess the thing is there is a lot of learning that can happen when you start going out and capturing data in the wild. So I'll hand off to, who's the next person?
I guess I'm next.
If you can get Jeff's slides up, please.
It's Geoff Mainland. I'm Geoff Mainland from Drexel University.
Please introduce yourself.
There we go. Okay. Thank you. So I'm Geoff Mainland from Drexel University, and I'll show a little bit for some of the things I've been working on. I do a lot of systems building. So I was the technical lead for our entry into DARPA's SC2 competition. I've been a heavy Coliseum user for many years. In fact, our radio is the only radio from the competition that you can use on the Coliseum. It's open source, it's available. I also work on our publicly available testbed at Drexel. So if you want to use our radio or our testbed, please come talk to me. I want to ask a question. It's a non-rhetorical question. It's meant to be interactive. I hope the answer is obvious. Do we value RF datasets?
Yes.
Show me. Don't tell me. Okay, so I'm going to tell you a couple secrets. You may discount everything I have to say after I tell you this. I'm a computer scientist, and in fact, my field is programming languages. So if you wonder what the heck I'm doing here, please come talk to me during dinner or during a break. I'm going to tell you what my home conference is. This is the secret. This is why you may discount what I have to say. It's the International Conference on Functional Programming. So I'm actually a Haskell person. So if you look at the call for papers for the International Conference for Functional Programming, you will see 2 interesting categories there. One is functional pearls. A functional pearl is an elegant essay about something related to functional programming. That's all it says. The other is experience reports. The purpose of an experience report is to describe the experience of using functional programming in practice, whether in industrial application, tool development, programming education, or any other area. So this community has said we value elegant expository papers. How do they show us that they value that? It's in the call for papers. You go to any ICFP and you will see functional pearls. This community has said we value real-world experience. How do they demonstrate that? It's in the call for papers. You go to ICFP, you'll see your experience reports from people in industry. The ACM has badges that reward people for artifacts, for replicated results, for reproduced results. How do we demonstrate that we value RF datasets? Well, when we're on program committees, when we're editing journals, when we're PC chairs, how do we make room in conference proceedings and journals for RF datasets to tell the community, to communicate to them, we value this work. As a systems builder, how many times, I cannot tell you how many times I've gotten feedback from reviewers that say, well, this is just engineering, right? It's not valuable, it's just engineering. This is just data set generation. How hard is it to go set up an SDR and collect some data? It's actually quite hard, isn't it? So we need to demonstrate that we value that. We also need to reward replication and reproducibility. Open data sets, open tools are great. Open results are really important as well. So what's so important about these open data sets? We can not only reproduce results for multiple papers that use these data sets, but we can compare them to each other because they are using these data sets. Right? That's the real power. So I would like not only a badge that says the results in the paper have been reproduced, but they have been reproduced with a publicly available data set. So you can go and compare this paper to other papers whose results have also been reproduced using the same exact data set. And you can go compare your own work to these other papers. So I'm gonna, I'm being facetious here. It seems like the overarching question of this workshop is, what is our ImageNet? Is that really the question we should be asking? And I don't think it's the only question we should be asking. RF is dynamic in ways that other applications are not. How do we recognize that? So I think we need a broader definition of data sets, right? We need, for example, reproducible RF scenarios. So let's take spectrum sharing as an example. It's great if I can go use a static data set to train an AI model that can recognize incumbents in spectrum. But what am I going to do with that model? I'm going to put it into a system then has to actually demonstrate spectrum sharing. How do I reproduce that result? So maybe I can go retrain some other model, compare my model to yours, but I want to compare my entire spectrum sensing and sharing solution to other solutions, right? So I need some sort of reproducible RF scenario as well. It's not enough to just have these static data sets to train AI models. Thank you.
Right. I'm Kumar Vijay Mishra from U.S. Army Research Lab in Adelphi, Maryland. Can I get my presentation here, please? Mishra. Okay, thank you. So we have been discussing about data sets for communications, and some speakers also talked about data sets for radar. And I work at the intersection of these two, what we call as joint sensing and communications, or joint radar communications, or integrated sensing and communications, or ISAC. So all the issues that we have been discussing for standalone communications and standalone radar, they all come together in these kind of systems. And the motivation for designing such systems is quite obvious these days. Pretty much every IEEE radar band these days has a coexisting communication services. So joint radar communications is not, it hasn't suddenly come to the arena. The very old papers we can see back in 1960s. And then in 1980s, low frequency radars used to encounter a lot of interference from TV and broadcast. But nowadays, with the advent of cellular communication, this interference that radar is encountering, so Monisha talked about interference in communications from radar. And here we are saying that all these important radar applications, they face interference from communications nowadays. So at L and S band, we have a lot of defense radar systems. On the civilian side, we have FAA radars, ARSR, ASR, and then we have National Weather Service radars, weather radars in the contiguous United States. We have 126 S-band systems. And in Canada, Europe, India, and Australia, there are C-band systems. And we also have FAA radar, which is TDWR operating at C-band. X-band, for the past 20 years, there has been a lot of applications, especially with mobile platforms for weather radars. And now we have automotive radars, or again, cloud radars at millimeter wave. with some applications going into the so-called sub-terahertz region. So there are a lot of these radar applications, and at the same time, we are also seeing communication. So the need is to actually design new systems where a common transmitter or common receiver may be used for that functions both for radar as well as communications. And there have been a lot of programs, as you can see some icons below in the slide, which were focused on a particular band, and these are at least 10 years old. But nowadays, we have been investigating these applications across all bands, especially at the higher frequency bands like millimeter wave or sub-terahertz. So depending on whether the transmitter or receiver is shared between radar and communications, we could classify these systems as broadly as I show in these 4 subfigures. So when we are not designing new radar and communication systems and they are operating independent of each other, but just trying to manage interference from one to another, then that is what we call as spectral coexistence. And the latest push is towards spectral co-design, where we would like to use common waveforms for both systems and even the common hardware units. So there are a lot of these different topologies, and based on this, some of the data considerations that we have, and I think Monisha talked about a lot from a communications point of view, and here these points that I've listed are from the radar point of view. And now you can see that, again, in radar as well, we have many different types of targets. Could be point target, could be volumetric like weather, could be extended target, for example, in automotive applications. Different types of waveforms may be used for a common system. It could be radar-centric waveform, COM-centric, or it could be a completely new waveform that needs to be designed. Terrain has to be accounted for in radar because clutter modeling is one of the very key feature of radar signal processing. Different polarizations and then different frequencies, like millimeter wave has a very different effect on precipitation compared to, let's say, S-band. And then geometry of deployment. In radar systems, for example, synthetic aperture radar, we have so many different geometries. There is tomographic SAR, there is circular SAR. So all these data sets, they become diversified with different types of use cases. Now, the data that are available to us, either we have security concerns from the government or DoD, so not the whole data could be shared, especially from the radar point of view. And then when we are doing joint sensing communications, then there are privacy concerns. Sometimes you cannot get data from automotive radar companies because they have IP concerns. And then even if you have a radar, for example, in universities, it's difficult to just start radiating all around because we have radiation concerns and we have to take it in secluded areas. In radar applications where human subjects are involved, for example, remote health monitoring using radar, their special permissions are needed. And sometimes when all of this is available, then we don't have IQ data which signal processing engineers need to design better filters or better receive processing, or there is a cost factor. For example, National Weather Service provides process data, but if you need more lower level data, then you have to pay for it. And in simulated data, like Monisha mentioned, there are all kinds of issues. Realistic target modeling is not there, and electromagnetic scattering models sometimes are not integrated. There are a lot of efforts towards standardization that are going on. In weather radar community, we have NetCDF metadata format that has been around for at least 15 years. Various societies which are concerned with radar applications, GRSS, AESS, or even Antenna and Propagation Society, have done some work on metadata standardization. Currently, I'm a vice chair of the first standards committee of IEEE Signal Processing Society on synthetic apertures, and we are trying to standardize some of these data sets from the synthetic aperture point of view. And then ComSoc has ISAC Emerging Technology Initiative, which has a working group on dataset generation for joint radar communications as well. I think they just started working on it. Some of the other data sets that I've listed, which are available from Air Force Research Lab on civilian SAR data sets. Then there's also something called cognitive radar data set. So we have some of those things available from government. And very quickly, I'll give 2 examples of some of the ongoing research that I'm doing. First is based on the simulated data set. So for example, when we want to use a communications protocol for sensing vehicular objects, in that case, sometimes we don't have data available from various automotive radar companies, and we have to do all this extended target modeling using different geometrical shapes, especially for pedestrian modeling. We integrate it with the electromagnetic scattering models. And then there is this software called PyBullet, which allows us to integrate the transmit waveform and the trajectory of the targets, and then generate a receive signal signature. And you could also integrate that with surface clutter models for, let's say, UAV-borne systems. A second example is where we use communication signal for aiding a radar observation. So for example, we are doing this project with a European telecom company where in many cases, because weather radars, they are big systems, they are not available everywhere, very expensive to install it. But the communications user terminals, from the satellite user terminals, are available relatively in many places and in huge numbers. So here, we had to deal with data from the telecom company, and they provided us some data that the user terminals had. We used it for rainfall estimation in a given region, and then we wanted to compare it with a radar. So the German Weather Service did not provide us the IQ data, they provided us just the process data, and that's how we could compare it. So we had to deal with some data issues both in the commercial domain as well as in the government domain. And then these are the kind of results we get. So on the right side, you see what the German Weather Service radar is looking at, a storm that is moving towards the northeast, and then what we get from the signals that were provided by this telecom data company. And then this is a very interesting area. We have been looking into many different applications. We have the distributed joint sensing communications. Terahertz has its own implications. So this slide just shows some of the exciting areas that this particular research is going on. And then finally, I'll finish with this. We have this book coming on, I and my colleagues that we have edited, Wiley IEEE Press, on signal processing for joint radar communications. And for other types of radar systems, we have a few other books, especially in weather radar, what kind of interference scenarios are there. So with that, I'll just end here. Thank you.
Thank you. So my name is Fatemeh Afgah. I'm from Clemson University. If I can please have the slides. Yeah, I don't see it here. So we had very good discussions today. I don't want to repeat the points that we have already talked about. I'm just going to talk about some of the challenges or the points that I have experienced during my own research. So we now have these wonderful power testbeds and cloud testbeds funded by NSF. What can we do next? To my perspective, one of the future research areas that we can emphasize on is going to be end-to-end data collections, and how we can connect these testbeds together, how we can have data from user to the cloud level. So we may not know all the use cases that this data can have for us, but we can certainly extend very new knowledge if we look at the network from that larger scale. So we obviously had less access to network level and control level data so far. The data has been just owned by the operators. Maybe in 5G, with having like ORAN type of experiments, we can have more knowledge on that domain. I think one other thing that the community can benefit from is going to be having some sort of unified user interfaces. So it's going to take a lot of time for the students and for the users to learn how to use each of these test beds. Then if we're going to connect these test beds, can we have user interfaces that are unified? Can these APIs be developed to a level that make it very easy for the users and the students to use them, like having some sort of like back scheduling between different test beds and having like APIs that can make it easier. One other point that Monisha also mentioned, I'm also thinking that the real data is going to be different from what we are collecting from the test beds. And collecting data from, for example, actual cellular networks is going to be very, very different. So there are different groups that they're individually collecting that data. Can we combine these efforts and having maybe combined data set in this domain? So by crowdsourcing here, obviously I don't mean collecting data but public. It's going to be a lot of privacy concerns, but privacy concerns aside, can we unify the tools and softwares that we are collecting these type of data, like there are XCal, there's Thames Pocket, Thames Investigation, and other software tools that are being used. But the data is not going to be easily integrated when they are being collected from different use cases. And one other point that Jeff mentioned, and I think it's very valuable, we are not used to collecting data sets that they are reproducible. So can we use some of the models that have been used in like CPS community or like biomedical domain to try to verify that data sets and having people to reference back to the work, so there is a good source of comparison. I think one recent resource of the community that I think it's going to be valuable is shown up by NVIDIA. I think that can provide some new opportunities for having reproducible research types. The focus of our research is collecting data for scenario-specific cases. So we had this discussion about, going backward. We had this discussion about having actual data and having synthetic data and how close they are, how we're going to compare the accuracy. So this is obviously for general cases. I believe synthetic data is going to be very valuable, but how about we have very specific scenarios? For example, we have like disaster management scenarios. Can we contribute to the community and collect that type of specific data? So one of the research that we are doing is focusing on cross-domain applications. So collecting RF data is one thing, looking it as a physical layer, having it as like a network layer and going up. I think we also need to make some efforts to combine RF data with data that is like related, for example, to autonomy, how we can combine decisions in terms of communication, resource management, path planning, coordination between the agents. So having data that are really heterogeneous, hierarchical, and they can contribute to having that higher level decision making. We're going to have very complicated multitask, multi-objective, multi-agent problem, but ML then really going to contribute to that type of problem solving. So for example, let's say that we're going to have like cellular connected drones. So the control committee is looking at, for example, path planning or coordination between the agents or collision avoidance. But in our RF community, we also understand that one problem for having this future like cellular connected drones is the coverage. It's like the throughput that the drone is going to experience, the amount of interference that is being caused to base stations. So can we collect data sets that can enable us to combine these decision-making objectives and come up with like multi-perspective solutions. I think that would be a domain that we can even contribute to advancing the AI model. So reinforcement learning has been used a lot by different communities. I think in our domain, maybe we can advance this in the sense that all the problems before they have been like mostly by known rewards. When we have this multi-perspective problem, we don't even know what is the good definition for a reward problem because the reward is coming from different aspects. So how we can, like, for example, use inverse reinforcement models or new models to find good solutions to model that type of like complex problem. One thing that I also think it's going to be valuable for the community is having simulators. So collecting that type of data, there are a lot of regulations. For example, the work that we are doing related to drones, having FCC license to have the drone to use cellular bands is close to impossible. There are certain labs like AirPod that they have that type of FCC license, but having that for a broader community is not very easy. So can we have simulators that can solve this problem at some extent? So we have very good physics-based simulators like Gazebo and Unity, but can we design new simulators that have an interface between network and communication and that type of like physics-based simulators to find some of these answer some of these questions at the simulator level? There are few efforts in the community to make that happen, but we still have a lot of room for new investigations in this domain. So just briefly, I wanted to mention our CCRI project that we are trying to make to answer some of these problems. This project called Discover is a collaboration between Northern Arizona University, Clemson, and Navajo Technical University. We have 5 sites in rural areas. So the focus of our research is addressing control, task management, distributed computing, and communication research in a heterogeneous testbed of drones, IoT nodes, and robots. And so we are trying to look at how communication and, like, for example, federated learning and local model development can be combined in a sparse and rural area. And one unique I think aspect that our group is offering is collecting data sets during actual disaster events. So for example, we are collecting drone-based images during prescribed fire. So obviously there is a lot of coordination and permission to work with USDA, US Fire Services, fire department to actually being able to fly drone even in a manual mode during prescribed fires. So that's the type of data set that we are recently collecting for the community. So this is a video from the test that we had in Arizona during prescribed fires. We have published the first version of Flame dataset. That this version is basically having like images of drone collected fire images using regular cameras and thermal cameras, and it has been a lot of effort to make these tests and like labeling the dataset and finding concrete ground truth labels. What we're gonna have in the next versions of Flame dataset is collecting LiDAR sensors, weather information sensors, and hopefully RF data. So we don't have a good understanding in terms of what we can share for RF data. And from the discussions today, I understand that my colleagues also have this question. So for our individual effort, while we have collected these data sets, we haven't had the permission or recommendation to make them public. But our effort is going to go toward finding the ways that at least we can publish some of these data sets. So in rural areas, for example, having a drone to operate kilometers away from the first responders' communication is the real challenge. Like developing, for example, LoRa-based communication systems that at least they can address command and control, not the payload. That's a problem to solve, finding the methods that how much of the data that we collect should be processed on the drone, how much should be shared, what kind of communication can actually be used. These are some of the questions that we are trying to address and hopefully making the data set available to the community. Thank you.
Okay, thanks. So as you say, there's a wide variety of projects and research that are using different kinds of data sets. So at this point, since we're running out of time, I'll open it up to the floor for any questions to any of the panelists. Go ahead.
Go ahead.
Yeah, mine is quick one. To any one of you who can answer the question regarding the dataset generation, especially on the software side. Are there standards on the software that we use in generating the data? Collection, yes, but we need to format, representing and put the data out for the public consumption. And I'm asking that question because probably I'm not in the area of the softwares and kind of thing. So I just wanted to understand if there are standards on the software to use?
Speaking for myself, I think a lot of it, there are no standards that I'm aware of. There may be, but a lot of it depends on whether firstly you're capturing data from a deployed network or whether you're capturing data from an experimental network. If it's a deployed network, many times you're limited by the tools you're using. And there are different tools out there, and at what level you are doing that. I personally have not done any RF captures, so if anybody has any input on standard, SIG-MF is the standard. I think that people are coalescing around for RF captures. But for example, if you're capturing LoRa data, you probably have a very different set of metadata that you're putting along with the data compared to Wi-Fi or cellular. And those are some of the issues I think we as a community need to work around as to, depending on what you're collecting, how do you annotate it, what are the standards? Any other?
So I do a lot of IQ data collection, mostly with USRPs, and there's no real standard there. We actually have decent standards, generic container standards like HDF5. People don't even use that, even though it's been available for a very long time. There are a lot of bespoke formats, so you'll see these data sets like radio ML data sets that are in completely bespoke formats. So there's no real standard.
Yeah, so I'll just talk from the radar perspective, and it's kind of the same situation as what you guys described. So as far as IQ data is concerned, depends on the application. It's not like that there is no standardization. As I mentioned in my presentation, for weather radar, we have NetCDF format for metadata and for processed moments. In SAR, there has been standardization of metadata as well. Automotive, I'm not aware if there is one particular standard, but if you're working with a particular company, they have just come up with some ad hoc standards of their own. So because radar is just so diversified, as is communications, really depends on what applications you're targeting at, but as long as you're in the same domain, there's a very high likelihood if a radar technology has been around for many decades in that particular domain, like weather or SAR, there are data standards for those applications at least.
Okay, I have a question. So one of the things that really enabled the data sets like MNIST and ImageNet and so on to really move their field was in part their clear utility and sufficientness of their size. So I don't think anyone looks at even the MNIST data set and says, no, I think I need a lot more numbers to really know what a number is, because people have a direct human interpretation that they can do. I think it's a real challenge for these RF data sets, as was raised in the previous panel as well. So I'm just thinking from the panelist perspective, what would it take, do you think, to have a data set of sufficient size, nature, and quality that would make it that when talking to an audience, the way that you can talk with an audience with ImageNet or MNIST, that it would be clear that that some approach has moved the ball? Like, what do you think is going to be as compelling? Or is it just the nature of RF that you think that's never going to happen?
Can I give an indirect answer? So one reason ImageNet did so well is because there was a competition, right? And performance improved over time. If we could have some sort of similar competition with an RF data set and demonstrate improvement over time, then we could say, yeah, that's a valuable data set, but how do you pick that data set to begin with, right? I don't quite know how to answer that question.
I agree, and I think one other point beside the size of the data is the object. So in image classification community, the problem was very clear, like object classification. In our community, there are a wider range of problems to solve. So if you're gonna look at the physical, is it modulation detection? Is it like interference detection? So I don't think we're gonna ever get to the point that we have like an ImageNet type of like data, but I'll see in other communities, for example, like in biomedical domain that I'm working, there are like annual competitions coming with a smaller size of data, but actually the focus is on the problem. So I see that like more coherent with what we are experiencing in RF community to define the problem beside the data set.
Yeah, I agree. I think one of the challenges in our community is communicating to the general public what is the benefit they get out of all of this data sharing and ML and everything else. So the network operators, clearly, they're doing their own thing. You know, they have the data of their networks, they're doing network optimization, and I'm sure they're getting value out of it. What is the value that the academic community brings to this whole play? Is it to the network operators? Is it to spectrum regulators by informing how spectrum can be used better? Is it to the end user by giving them a better quality of service? I think in many ways it's still early days for data and wireless, and we are still trying to feel our ways as to where is the application where we're going to make the best impact. But I think we have to get there. Otherwise, we're not going to have impact, right? And maybe it is that we pick a few examples, we run these kind of competitions that motivate students. I think the DARPA SC2 challenge was great in doing that. They picked a very defined, and you may argue that it wasn't a very realistic situation, whatever, but at least it galvanized the community around something that caught their imagination. And we need to probably figure out, and maybe RFDataFactory, that's one of your first tasks, is to come up with a competition where we look for the best application for an RF data set.
Good feedback. I'm taking notes for sure. Other questions?
So can I just add to
sure.
that, again, from the radar perspective? So yeah, I completely agree that these kind of competitions, they do help. For example, a lot of SAR data, there are a lot of these NASA contests. There are millions of SAR images available, and they ask students to go through them and if they could identify new objects that have not been seen before. And it ran for many, many years, that competition. Although I did not see it translated as to the number of publications because these were students who were using these. But you take AFRL SAR dataset, which a lot of these days I'm seeing a lot of automotive radar-related publications are using. So that was quite successful, although there wasn't any competition. But at the same time, it has also become outdated very quickly because they were recorded at a frequency which automotive radars are not using these days anymore. So we also have that issue. All this data that are recorded, after some time, at least from the remote sensing perspective, they become outdated.
Yes.
And so much effort that goes into that is...
Cats stay the same. Cats and dogs, the images don't change over time as much as the RF environment does.
True.
So that is quite a challenge that we face as a community in terms of...
Yeah, hi, Paul Niklich. I'm the chair of IEEE 802, and I've been listening very intently all day. This is an area that I'm not familiar with, but it seems to me, somebody said what's important is that there needs to be clear utility and a well-defined application. To me, an area that absolutely can benefit from focus would be the next generation of 802.11. which we're right now in the midst of thinking about defining. So is there a way to focus the work that you're doing on that particular area? That would be high utility, and it's very specific.
So how do we engage with that as this community? If you can give us a little bit of insight.
Well, we're right in the middle of trying to figure out what it is, and we have meetings, regular meetings, 6 times a year. The next meeting we have is in July, and these discussions are taking place in the wireless next generation task group in 802.11. And it's open, and because of COVID, we're we've been fully remote. Now we're going to hybrid in July. But, you know, I would say engage with that wireless next generation group that's discussing that today. We just started it a couple of sessions ago, and it's ongoing activity. As a matter of fact, Francesco Restuccia, I don't know if he's here today, is participating in that activity. So that's how to do it.
Yes, and I've participated a lot in the coexistence workshop, in the coexistence group.
Right, you were part of that, you know, back in
the Wi-Fi
Austria.
LAA, and you know, I've taken a lot of our measurement work in there, and that's definitely a nice way to engage. And I know that right now 6 gigahertz and spectrum sharing in there is still a topic of discussion.
And this is a gap I've been trying to close the last couple of years, the gap between academia and the commercial activities in 802. I mean, 802 is very, very commercial oriented, and there's the pace at which we operate is relatively slow compared to, you know, what academia may want. Or it's also very consensus based. So you can't just come in with a single presentation and say, here's my gem, go and use it. No, you've got to prove that there's value and utility in that particular asset that you're bringing to 802. And that's somewhat incompatible with my perception of how academia works. And I'm trying to resolve that, and I'm working with Francesco to try to resolve those issues.
I think that's commendable. I think more of us need to be more involved and engaged. And I think this is certainly a message we should reinforce in the feedback from the bookshop.
I think focus is key for you guys.
True. So just in the interest of time, thank you very much to the panelists. Just a quick shameless plug-in for the data set that Fatemeh described, the one on Flame. That's one of the most downloaded data sets on Elsevier computer networks. For some reason, I was the editor that looked into the data set. But the thing is that this is appreciated. These data sets are valued. So there are venues where you can publish data sets just for the data set contribution alone. For example, Elsevier Computer Networks has a track on data sets. So thanks for the contribution and for mentioning that. So what we're going to do now is we're going to do yet another of those breakout sessions. We have the same 2 rooms, and we have 2 lead persons who will assist in capturing notes. If I can please ask you to make your way into these smaller group meetings, into the adjoining rooms, and I'll request the panelists here to sort of oversee the discussions in the 2 different groups.